Good evening everyone. My name is Devlina Maiti. I am a NPTEL TA for the course Basic Real Analysis under the course instructor Professor I. K. Rana. Now in the last session we have started Riemann integrability. Right? So a function f, first for Riemann integrability the function f needs to be bounded on that interval. So f is bounded on this interval AB. Then we have taken a partition P be a partition of AB. That means P belongs to this class PAB, which is the set of all partitions of this interval AB. Right? Then we have defined UPF and LPF. So what was UPF? So UPF was the sum of MR XR minus XR minus 1. Where this partition P is suppose x1 to x0 to xn. This means x0 is A and xn is B. And this MR, capital MR is the supremum of fx in this interval, sub-interval xr minus 1 to xr. Right? This is the upper Darboux sum of f with respect to this partition P, and LPF was this sum small mr into xr minus 1, where this small mr is the infimum of f in this interval, sub-interval xr minus 1 to xr. Right? So mr is supremum of fx in xr minus 1 to xr and infimum of fx in xr minus 1 to xr. Right? And we have seen that m into b minus a is less equals to LPF, which is less equals to UPF, where this small m is the infimum of fx in the whole interval AB and capital M is the supremum of f in the whole interval AB. Right? So what we are doing is then we have taken the supremum of, we have defined this A to B F to be supremum of LPF over the whole partitions, all the partitions of AB, and this was the infimum of UPF. Right? So what we are doing is that we are, when these two are equal, this upper sum of f, upper integral of f and the lower integral of f is equal, then we say that f is Riemann integrable. So we are getting this is when this is become closer, so we are taking the supremum of this LPF and infimum of this UPF. So we are making these two closer. Right? And when these two are equal, these two, so when this two is equal, then we say f belongs to RAB, means f is Riemann integrable in this interval AB. Right? And we have also defined what is a refinement of a partition. So Q is a refinement of a partition P if P is a proper subset of this Q. Right? Okay, we'll start with a result. So it says so f is bounded and P and Q be any two partitions of AB. Right. Then we'll see that the lower sum is less equals to UQF so the lower sum is always lesser equals to the upper sum for any two partition. Right. So first we'll prove this. So in refinement we have seen that when we do a refinement, the lower sum will increase and the upper sum will decrease after refinement, right? So we'll use that property of refinement. So first take this P S equals to P union Q. So S will be a refinement of P as well as Q, right? So S is a refinement of P as well as Q, right? So now LPF is less equals to LSF because after refinement lower sum will increase, right? And LPF is always less equals to UPF, right? This one. So this is less equals to USF and after refinement the upper sum decreases. So this is less equals to UQF. We can write it, right? Because S is also a refinement of Q. And similarly LQF is less equals to LSF, which is less equals to USF, and since also S is a refinement of P, so we can write, okay. So what we have? So this is the proof. So our LPF is less equals to UQF and LQF is less equals to UPF, right? Okay, so this is done. Now what we have here is that the lower sum LPF is always, so we had this m into p minus a less equals to right, and then we have defined the upper integral of f and lower integral of f, and that also, this means this a to b f and the lower sum both are in between this, right? Because they are the supremum and infimums, so they also are bounded by these two numbers, right? Now we will prove that the lower sum of f is less equals to the upper sum of f, right? This we are going to prove now. And for this proof we'll need this result. So theorem 1 says, let f be bounded on AB, then the lower sum of f is less equals to the upper sum of f. Right? So first we will take any two partition of AB. So let P and Q be any two partitions of this AB. Okay. Then by the above result, what we have? We have LPF is less equals to UQF. Right? Now if we fix Q, then this, now if we fix, so fixing Q, if we vary P over PAB, right, then this inequality holds for all the partitions P, right? Then if we name it, now if we're fixing Q, we see that one holds for all P belongs to this PAB, right? Because P and Q are arbitrary, right? So this means this UQF is an upper bound of, so this means what? This means this UQF is an upper bound of this set LPF where P varies in PAB, right? So this is an upper bound of this set, and the supremum of this set is what? Supremum of this set is also the supremum of this set, or the least upper bound, the least upper bound of this set is this number, right? And UPF is an upper bound of this set, so this will be, so this means this is less equals to UQF, right? Because UQF is an upper bound, and this AB to F integration, this is the least upper bound, the suprema. So this will be less equals to UQF, right? Now this number, the left hand side, is a fixed number. It does not depend on the partition, right? So, and here if we change Q, since this is true for arbitrary Q is fixed but arbitrarily, right? So this means this, if we take this set now, then this AB to F is a lower bound of this set, right? Then this set has a lower bound which is A to B F, right? This is a lower bound. And what is the greatest lower bound? That is the infimum of this set is what? And bound, and this number is the greatest lower bound of this set, right? This is the greatest lower bound right? So this will imply less equals to A to BF, right? So hence this theorem is proved. So the lower sum is always less equals to the upper sum. So now we have this inequality. This is less equals to right? Okay, now we'll see one example. We prove that the identity function fx equals to x is Riemann integrable, and we'll find the lower sum and upper sum. Okay, is defined by fx is equal to x then prove that f belongs to RAB, that is f is Riemann integrable. So we have to prove this by showing both the upper sum and lower sum are equal. Okay. Also you have to evaluate the number this, right? So f is bounded on AB, right? Now take this partition Pn to be A and the last one is A plus in H, where H equal to B minus A by N. So Pn divides AB into n subintervals, equal subintervals, right? Now what is MR? Capital MR is supremum of fx in this interval xr minus 1 to xr, right? And small mr is infimum of fx when x belongs to this interval, right? Now this f is a increasing function, right? So fx is x, so f is monotonically increasing. increasing in this interval. So MR will be, since it is increasing, so capital MR will be f of xr, right? And what is this? This is a plus RH, and small mr will be f of xr minus 1, that is a plus r minus 1 h, right, for r equals to 1 to n. Okay, now we'll calculate UPF and LPF. So UPNF is what? This is MR into XR minus 1. So the first one is A plus H into H, like this. So A plus NH to H, and this will be H into A plus so this is simple calculation. So if we use this relation, so this relation, this NH equals to B minus N. Okay, so if we use this relation, we'll have this is B minus A into A plus half into square into 1 plus 1 by n. Okay, using this relation. Now similarly, if we calculate LPNF, then we'll get H into right. So this is so finally we have this 1 minus 1 by n, right? So we got UPNF and LPNF, right? Now supremum of this set, so you have to take supremum of LPF, LPNF and infimum of UPF, right? So supremum of LPNF now Pn are some particular partitions, right? So this supremum will be less equals to supremum of this set LPF, where P belongs to this partition, right? So in the right hand side we have over all the partitions, and in the left hand side some particular partitions, right, where they are equally distant, the subintervals are, right? So this supremum will be less equals to this supremum, and this supremum of this left hand side is what? This means when n goes to infinity. So when n goes to infinity, the intervals become finer and finer, right? So the supremum is then, see that this supremum will be B minus AA plus square by 2, and the right hand side is what? The right hand side is this number, right? So it is actually right. So we got this relation, Now let's go to the UPF. So we are taking infimum of this, right? So infimum of this UPNF will be greater equals to infimum of UPF, where P belongs to PAB, right? Because the right hand side, the set is bigger, so the infimum is lesser. So this implies this value is same, and this value is what? This is the upper sum of f. So we have right. So we have these two relations. Now from the previous theorem, what we have? We have the lower sum of f is always less equals to the upper sum of f. Sorry, the upper integral of f, right? And from these two relation, we have this lower integral is greater equals to b square minus a square by 2, and from the last relation we have this is less equals to b square minus a square by 2, right? Using theorem 1 and these two relation, we get this one. Now both these two are the same number. So by sandwich theorem, since these two are equal, so all the values in between them must be equal, right? So this implies equal to b square minus a square by 2. So this upper integral and lower integral both are equal, and they are equal to this value b square minus a square by 2. So this means the Riemann integral a to bf is equal to this b square minus a square by 2. So we have proved that this fx equals to x is Riemann integrable, and the value of this integration is b square minus a square by 2, right? Okay, now we'll define a condition for integrability, right? So let f be a bounded function. So let f be a bounded function on this interval a. Right. Then f is integrable on AB if and only if for each epsilon greater than 0, there exists a partition P belongs to partition of AB such that this UPF minus LPF is less than epsilon, right? So you say that f is integrable on AB if and only for a given epsilon there exists a partition P for which this inequality UPF and LPF are closer. The difference is less than this epsilon, right? Then we say that f is Riemann integrable. Now we'll define norm of a partition. Now what is norm of a partition? So let this AB is closed bounded interval. Right, and P be a partition of AB. Let P equals to be a partition of AB, right? Then we define norm of P to be the maximum of these numbers, these differences, xn minus xn minus 1, right? So norm P is this means norm P is the maximum length of the subintervals into which this partition is divided, this AB is divided. So the maximum length of the subintervals into which this AB is divided by P, right? This is the definition of norm of a partition. Okay, now there is a result for Riemann integrability. So this is theorem 2 says, so let F be a be bounded on AB if Pn be a sequence of partitions of AB such that norm of Pn goes to 0 as n goes to infinity, right? Then what we have limit n tends to infinity, UPNF is actually the upper integral, and limit n tends to infinity, LPNF is the lower integral, right? So this is a very important theorem. Okay, now I'll use this in an example. So let f is a function defined by fx equals to x when x belongs to, when x is rational and 0 otherwise. Okay. Then we have to find the upper sum and lower, the upper integral and lower integral of f. And we have to deduce if it is Riemann integrable or not. So we'll see that this also we have to prove that this f does not belongs to R01, means f is not Riemann integrable, right? Now to prove this, first we will take a sequence of partitions. So we'll apply theorem 2 here. So to apply theorem 2, we have to take a sequence of partitions, right? So we'll choose this partition, this sequence of partitions, which is Pn equals to 0, 1 by n to n by n, right? So this is a partition of sequence of partition, right? So if we change n, so Pn belongs to P01, right? So this is a partition of 0, 1. Now for this partition we will find out UPNF and LPNF, right? So for this we have to find first MR, which is a supremum of fx when x belongs to this r minus 1 by n to r by n, right? Supremum of this number. Okay, so what we are doing is that we have to check that this function f is not Riemann integrable, and for this we have to use, we'll use this theorem 2, where we will find a sequence of partitions Pn whose norm will go to 0, and we'll see that the upper Riemann integrable, upper integration, this one and this lower integral, both are different, and then we'll see that this f is not Riemann integrable. So first we have chosen this partition Pn, which is 0, 1 by n to n by n, right? Now for this partition we'll find the upper integral and lower integral. So for this, first we have to find this capital MR, which is supremum of fx when x belongs to this subinterval r minus 1 by n to r by n, right? So what is this number? So fx is x when x is rational and 0 otherwise, right? So in this interval, the supremum value of fx will be what? The supremum will be r by n, right? Because only in the rationals they are giving non-zero terms, and r by n is rational, so at r by n it will be the maximum value, which is r by n, and small mr is infimum of fx when x belongs to this interval r minus 1 by n to r by n. So the infimum value will be 0, because in rational it is positive value and in irrational it is 0. So the infimum will be always 0 in each of the subintervals, right? So now we have to calculate UPNF. So UPNF is what? It is the sum of MR into XR minus 1, right? So it is M1 into, so the first is 1 by n minus 0, and the last one will be Mn into, sorry, this one. So each of this is 1 by n, so we'll take 1 by n common, and M1 is R by n. So the first M1 is 1 by n, and the second is 2 by n, and the last one is n by n, right? And this value will be this n plus 1 by 2n, right? This will be UPNF, and LPNF is basically 0 because all the MR, small MR are 0. Now we will let n tends to infinity, right? So limit n tends to infinity, UPNF is actually, by our theorem, if when n tends to infinity, UPNF is this is the upper sum. So UPNF is 0 to 1 f, which is half, right? And n tends to infinity, LPNF is the lower integral, which is 0. So these two are not equal, so f is not Riemann integrable. So f does not belongs to R01 S, right? So this function is not Riemann integrable. Now there is another criteria to check Riemann integrability. So this criteria depends on epsilon delta definition, right? Like continuity and differentiability. So let f is a bounded function. So f is bounded, then f is integrable on AB if and only if for each epsilon greater than 0 there exists delta greater than 0 such that UPF minus LPF is less than epsilon for every partition P of AB satisfying norm P less than delta, right? This is the epsilon delta definition. So the first criteria was what? This was f is integrable if and only for given epsilon greater than 0 there exists a partition such that this difference UPF minus LPF is less than epsilon. So you have to find a partition for this, right? Now in this condition given epsilon greater than 0, we have to find a delta greater than 0 such that this inequality holds whenever norm of P is less than delta. Right? Okay. Now we'll use these definitions, these criteria, to prove that a monotone function and a continuous function are Riemann integrable. So all the monotone function and continuous function will be Riemann integrable. So the first is so f is monotone function. Now I'll prove this one. So without loss of generality, let's take f is monotonically increasing. Right. So let f be monotonically increasing on AB. Okay. Now choose. Now since f is increasing, so fa is less equals to fb, right? This means fb minus fa is greater equals to 0. Right. Now choose an epsilon greater than 0. Now we have to find a delta depending on this epsilon, right, for which this inequality holds. Right. So let P be any partition of AB. So first choose delta. So epsilon is given. Now we'll take delta to be epsilon by plus 1, because fb minus fa it may be 0, right? So since we are taking in the denominator, so that's why we are adding by this 1, capital 1, right? Now we'll see that why we have taken this delta to be this number, right? Now let's take P a partition. Let P be a partition of AB with norm of P is less than delta, this delta, right? Norm of P less than delta means all the subintervals, length of these subintervals is less than delta, right? Now P this one means it means a equals to x naught, this is less than x1, and so on, this is less than xn, which is b, right? Now what is mr? Mr is supremum of fx when x varies in xr minus 1 to xr, right? Now our f is monotonically increasing, so the maximum will be attained at xr, right? So supremum is actually f of xr, and mr is infimum of fx when x belongs to this interval xr minus 1 to xr, and it is monotonically increasing, so the infimum value is xr minus 1, right? Now what is UPF minus, you have to calculate this one, right? You have to check this is less than epsilon when norm of P is less than delta, right? where this delta depends upon epsilon. Epsilon is already given. So this number is what? This is capital MR minus small mr into XR minus XR minus 1, right? Now our norm P is less than delta, right? Norm P is less than delta, means each of the subinterval, norm P was what? Norm P was maximum of this x1 minus x0, x2 minus x1 to xn minus 1. Length of all the subintervals. Maximum is less than delta. This means all the subintervals are, length of all the subinterval is less than delta, right? Now xr minus 1 will also be less than this delta. This means xr minus 1 is also less than delta, which is epsilon by fp minus fa plus 1, right? So then from this inequality, from UPF minus LPF, so since this happens, this xr minus n is less than delta for all r equals to 1 to n, right? So we'll bound it by this number epsilon by plus 1, right? And the left is mr minus small mr, right? And what is this value? Capital MR is f of xr and small mr is f of xr minus 1, right? Now if we add this f of x0 minus f of x1 like this, then it will be cancel out. So it is what? It is fx1 minus fx0 plus f of x2 minus f of x1 and so on. We have f of xn minus f of xn minus 1. So all of this what? I didn't get your question. Yes. So we have already proved that this capital MR is actually f of xr and small mr is these two, and small mr is f of xr minus 1 because it is monotone function. That's why. Okay. So since it is monotone, this capital MR is f of xr because supremum is attaining at the right end, right? It is monotonically increasing, we have chosen. That's why capital MR is f of xr and small mr is infimum. So infimum will be attained at the left end point. So that's why small mr is f of xr minus 1, right? So this will be cancelled out and we will have one into f of xn minus these two are left only, and xn is b and x0 is a, so it is fb minus fa, right? Now this value is less than 1, this this term, because this is the numerator is fb minus fa and the denominator is fb minus fa plus 1, right? So this is less than 1 means, so this value is less than epsilon. So what we have proved is that first we have chosen an epsilon greater than 0, then depending on epsilon we have chosen our delta, and we say that if P is a partition for which this norm is less than delta, then we have proved that this UPF minus LPF is less than epsilon, right? So this satisfies this criteria, right? That's why f is Riemann integrable. So any monotone function is Riemann integrable. This implies f is integrable on AB, right? Now we'll prove that if f is a continuous function, then also f is Riemann integrable. So this is our next theorem. So our f is bounded and continuous. We don't need to say it is bounded, since it is continuous on this closed bounded interval, it is bounded, right? Because continuous function maps compact set to compact set. So we don't need to say it is bounded now. So if P only continuous is enough. Continuous on AB. Then f is Riemann integrable. So all the continuous functions are Riemann integrable function. So we'll prove this. So f is continuous on this closed bounded interval. So this means f is uniformly continuous on this interval, right? Because this is a closed bounded interval. So f is uniformly continuous on AB, right? Now since it is uniformly continuous, for the epsilon delta definition, this delta will depend only upon this epsilon, right? Not on the point. So given epsilon greater than 0, there exists delta greater than 0 such that for any 2 point, whenever x minus y is less than delta, we will have fx minus fy is less than epsilon, right? Means this delta does not depend on the points, it only depends on epsilon for uniform continuity, right? Now we'll take a partition. Now let P be a partition. P partition of AB with norm of P less than this delta. The delta coming from this uniform continuity, right? So for integrability we have to find a delta for given epsilon, right? So we are choosing this delta. So P is a partition with this condition. Now what is MR? MR is supremum of this okay, I have not taken P, so let P be x1 to xn, right? P is this partition. So capital MR is supremum of fx over this interval xr minus 1 to xr, right? Now since f is continuous, so the extremum value will be attained, right? This means there must be a point in between this interval. At this point the supremum occurs, right? Since it is a continuous function. So say MR is infimum. Now since f is continuous, on this closed bounded interval, so the extremal occurs, right? Supremum of f and infimum of f is attained. This means what? This means there exists some zeta r belongs to xr minus 1 to xr such that capital MR is actually f of zeta r, right? This means supremum occurs in this interval, right? Actually supremum here is the maximum, right? And there exists some eta r. This is a property of continuity such that this infimum value is attained. Means there exists a point for which f of eta r is the infimum value, this small mr, right? Now P is a partition with norm P less than delta, and this norm P less than delta means mod of length of this xr minus 1. This is also less than delta because supremum of this value is norm P less than delta. Now these two numbers zeta r and eta r both belongs to this interval, and length of this interval is less than delta. This means the difference of these two numbers is also less than delta, right? As norm P less than delta, right? Now from uniform continuity, what we have? Whenever x minus y is less than delta, we will have fx minus fy is less than epsilon. So now this zeta r minus eta r is less than delta, so this will imply f of zeta r minus f of eta r is less than epsilon. Okay, let's take here not epsilon, we'll change it from epsilon to epsilon by b minus a, okay, for simplicity in the last calculation. This is same thing, epsilon is greater than 0 means b epsilon by b minus a is also greater than 0, and for that value we can find a delta, right? So here epsilon is epsilon by b minus a. Okay. Now what we have to find? UPF minus LPF. So we have found MR and capital MR and small mr, which is f of zeta r and small mr is f of eta r. Now we'll find UPF and LPF. So we have to find this difference UPF minus LPF, right? And this is equal to MR minus small mr, right, for r equals to 1 to n. Right? Now each of this value xr minus 1 is less than delta, right? And for this we have found this f of zeta r minus, okay, I am writing this as mr. We have found what? F of zeta r, and small mr is f of eta r, right? xr minus so there is no need to take this mod, because f of zeta r is the maximum value and f of eta r is the minimum value, right? So using this relation, what we have? We will have this is less than b minus a, and the left is xr minus 1, right? Now what is this value? This is x1 minus x0 and so on. So we will have epsilon by b minus a into xn minus, this will not cancel out, xn minus x0, which is b minus a, right? So this is actually epsilon. So we have found a delta for which whenever norm p is less than delta, this UPF minus LPF is less than epsilon, right? So this implies f is Riemann integrable by the above condition, right? This condition. So if f is a continuous function, then also f is Riemann integrable, right? Now we'll see some examples. So let fx is the box function. Okay, first I have to derive some result. So we'll see that if f is not continuous but it is piecewise continuous, means it is continuous except for some finite points, then also it will be Riemann integrable. So I will state these theorems. So let a function f from AB to R be bounded and let f be continuous AB except for some finite values, except for a finite AB, then also f is Riemann integrable. So this theorem say f need not be a continuous function, but it is piecewise continuous. It is continuous except for some finite number of points in that interval, then also f is Riemann integrable. And there is another theorem that if f is continuous except for a infinite number of points, then what happens? So let f be bounded on a B and let f continuous on AB except on a infinite subset S of AB. So now it is not finite, that number of discontinuity is infinite. So S of AB such that the number of limit point of this set S is finite, then f is Riemann integral. So this theorem says if f is continuous except for an infinite number of points in AB, and if the limit point of that set is finite, then f is Riemann integrable, right? So I am not going to the proof of these theorems. So we'll see some examples. So these theorems are useful to identify if a function is Riemann integrable or not, right? This will be quick to judge. So our f is a box function in 0 to. So we have to check if it is Riemann integrable or not. So what is this function? So this is actually 0 when x belongs to 0 to 1, 1 when 1 to open to, and 2 when x equal to 2, right? This is the function. So this is actually so from 0 to 1 it is 0, it is 0 not 1, and from 1 to 2 it is 1, and at 2 it is 2, right? This is value is 1, this is open, and at 2 this value is here, this is 2, right? So the discontinuity is at the point 1 and 2, right? Point of discontinuity. So f is continuous on 0 to 2 except for x equals to 1 and x equals to 2. So this number is finite. So by this theorem 5, f is Riemann integrable, right? Except for a finite number of points. So by theorem 5, f is Riemann integrable on 0, 1. Right. Now take this function which is defined by f0 equals to 0 and f of x equals to 1 by 2 to the power n minus 1 when x lies between this value. For n equals to 1 to infinity. Now you have to check if f is Riemann integrable or not. Right. Now how does it look like? This is 0, this is our 1. 1 by 2 square, right? Now from half to 1, so n is 1, right? So now when x belongs to n is 1, so when x is lies between half to 1, so what we have? We have fx equals to 1 by 2 to the power n minus 0, that is 1, right? So in half to 1, it is 1. So if it is 1, then half to 1, it is 1. Right? So this is open. At half, we don't know the value. Okay, this was equal to in the left, right. So at 1 it is 1, right? But at half it is 1 by 2 to the power n. So when 1 by 2 square less than x less than 1 by 2, we have this value 1 by 2, right? So from 1 by 2 square to half, it is half, right? Open at 1 by 2 square, right? And it will be 1 by 2 square when it is this one and this one like this, right? So you can clearly see this function f is monotonically increasing, right? It is a step function. So this function is bounded, because for Riemann integrability first it has to be bounded, right? So f is bounded and it is monotonically increasing. So by this theorem, theorem 2, theorem 3, if f is a monotone function, it is Riemann integrable. So this function is Riemann integrable, right? Okay, let's see another example. So f is a function defined by f0 is 0 and fx equals to minus 1 to the power r minus 1 when x belongs to this 1 by r to 1 by r plus 1. For r equals to 1 to infinity. Then we have to check if it is Riemann integrable or not. So if you look at the graph, so 1, 4 like this. and the value oscillates between 1 and -1, right? Fx is -1 to the power r minus 1. So this is 1, this is -1. Now if f lies between 1 to half, if r equals to 1, then fx is 1. So r equals to 1 means it lies between half to 1. So half to 1, the value is 1. This is open. And from 1/3 to 1/2, if r equals to 2, then the value is, so when r equals to 1, this is half to 1 and fx is 1. And if r equals to 2, it is 1/3 to 1/2 equal to 1/2, and the value is -1, right? So then the value is -1. Open at 1/3, and again from 1/4 to 1/3 it will be 1, and from 1/5 to 1/4 it will be -1, like this, right? So the point of discontinuity are what? So f is discontinuous at x equals to what? X equals to half, 1/3, at 0 also. So 0, half, 1/3, and so on, right? So the set, let's S be this set. So this set is the set of discontinuous point of f, right? So what is the limit of this set? Limit point, the limit point of S is what? This is a singleton set which is 0, right? If it is another sequence, the limit point may be 1 or 2, may be finite, right? Now for this set the limit point is 0, and this theorem 6 says if f is discontinuous on a infinite number of point of S, and the set of the number of limit points of S is finite, then f is Riemann integrable, right? So here f is not continuous, f is discontinuous, and the point of discontinuity is infinite, but the limit point of this set S is finite, which is the singleton 0. That's why by theorem 6 f is Riemann integrable, right? Okay. Now prove a property or theorem for Riemann integral. So we say that if f is Riemann integrable, then mod f is also Riemann integrable. So f is a be bounded, be integrable means it is bounded, integrable on AB, then mod f belongs to RAB, means mod f is also integrable on AB. Now mod f means what? Mod f means if fx is negative, it is minus fx. Okay, I'm writing this. So Mod f means mod of fx. This means fx if fx is greater than 0 and minus fx if fx is less than 0. Right. This is mod f, the function. Now f is Riemann integrable, so f is bounded, right? Now f belongs to RAB, so implies f is bounded. Now f is bounded means mod f is also bounded, because mod f is what? Mod f of x is actually mod of fx, which is less equals to some k, as f is bounded. So this implies mod f is also bounded. Right. Now f is Riemann integrable. This means given epsilon greater than 0, there exists a delta, or there exists a partition. P of AB such that UPF minus LPF is less than epsilon. Right. So since f is Riemann integrable, by the condition given epsilon greater than 0, there exists a partition P such that this inequality occurs for this partition. Right. Now let P, we are taking P to be this partition. Right. Now what is MR? MR is supremum of fx in xr minus 1 to xr, and small mr is infimum of fx in this interval xr minus 1 to xr. And let capital MR dash is supremum of mod fx, this function, in this interval, and small mr dash is the infimum of this function mod fx in this interval. Right. Now for any two points, alpha beta in this interval xr minus 1 to xr, what we have? We have mod f of alpha minus mod f of beta is actually mod of f alpha minus mod of f beta, right? And by triangular inequality, this is less equals to what? This is less equals to f alpha minus f beta, right? So we'll need this. So this is, say, suppose 1. Right. Now we'll use a result So this result is what? This is a simple exercise. You can do it on your own. Okay. If S is a non-empty set, if S is a non-empty bounded subset of R with supremum of S is capital M and infimum of S is small m, then the supremum of this set is what? This set mod x minus y, where xy belongs to S, is capital M minus small m. Okay, so this result we are going to use. So this result says, if S is a non-empty bounded subset of R, where the supremum and infimum is M and small m, right? Then the supremum of this set mod of x minus y, where x and y varies in S, is capital M minus small m, right? So we are going to use this result. So here our F was bounded, so for this problem our F is bounded on this subinterval xr minus 1 to xr, right? And supremum of this set is capital Mr. Supremum of fx is capital Mr in this interval, and infimum is small mr. So supremum of this set by this result, using this result, the supremum of the set mod of f alpha minus f beta, where alpha beta lies in this interval, is what? Is capital Mr minus small mr, right? Using this result. And similarly, mod f is also bounded on xr minus 1 to xr, and the supremum and infimum are capital Mr dash and small mr dash, right? So using this result, the supremum of the set mod of f alpha minus where alpha beta belongs to this subinterval is this one, right? And from this inequality 1, what we have? From inequality 1, the right hand side was mod of f alpha minus f beta, right? And we have found that mod of f alpha minus f beta, the supremum of this set is capital Mr minus small mr. So this, in 1 we'll get this is less equals to capital Mr minus small mr, right? So from 1, what we will have? We'll have f beta is less equals to mod of f alpha minus f beta, which is less equals to capital Mr minus small mr, right? So capital Mr minus small mr is an upper bound of this set, this mod f of alpha, mod f of beta, and the supremum value is this one. This is an upper bound of this set, right? And the supremum is this number. So the supremum is also less equals to this upper bound. So this implies capital M r dash minus small m r dash is less equals to this, right? As capital M r dash minus small m r dash, this number is the supremum of this set. And capital M r and minus small m r is an upper bound. Right? So we have found this one. This is say 2. Now we will prove that UPF minus LP, okay, UP mod F. So now what we have to find? To find UP mod F minus LP mod F is less than epsilon, right? Now what is this value? This is m1 dash minus small m1 right? Right? Because m1 dash are the supremums and small m1 dash is the infimum, right? Now what we have from 2, this is this mr dash minus small mr dash is less equals to m1 minus small m1 of x1 minus x0 to mn minus so this is xn minus 1 to xn, right? And this number is what? This is UPF minus LPF, right? Because this capital M is the supremum of fx in this interval. So, and this f was Riemann integrable. This f was Riemann integrable. So UPF minus LPF was less than epsilon, right? So we'll have this is less than epsilon, right? So this means we have found a partition for which this UP mod F minus LP mod F, this number is less than epsilon. So this implies F is mod F is also Riemann integrable. So if F is Riemann integrable, mod F is also Riemann integrable, right? But the converse is not true. So note that if mod F is Riemann integrable, does not implies F is Riemann integrable, right? So you have to give an example. So the example is, if we take this function fx to be 1 when x is rational and minus 1 when x is irrational, then what is mod F? Mod F of x is 1 for all x belongs to AB. So it is a constant function, so it is Riemann integrable. So mod f is Riemann integrable. But this function f is not Riemann integrable. If we take the upper sum and lower sum, that will be different. So this condition is sufficient but not necessary. So if f is Riemann integrable, then mod f is also Riemann integrable. Right? Okay, so I will end this session here. Okay, thank you.